Are you ready to be introduced to yet another carbon nucleophile? Because here we go. Wow, look at how much we've covered already. The big overview, addition of hydrides, addition of carbon nucleophiles that are organolithiums or Grignards, and now another carbon nucleophile, Ylides. So, we'll do a quick overview, then look at two examples of Ylides that are particularly useful for organic synthesis. The Vinegar and sulfonium ylides to make epoxides. So, Ylides, pretty cool word. Basically what it amounts to is an ylide is a reagent, as shown here, that has two atoms adjacent, one with a positive charge, one with a negative charge. Since this is organic chemistry, we're interested in ylides that have a carbon anion. So they're really not as strange as you might think. This is thiamine pyrophosphate. It is the biochemical ylide. And if you look right here, oops, not right there, I tell you. There's always something. Right there, you can see there's the carbon anion adjacent to the positively charged nitrogen. But the ylides we're interested in are these two. A phosphonium ylide, that is the key player in the Vinegar reaction, and a sulfonium ylide. So, what to point out here is the very important resonance contributors that show how these negative charges on the carbon can be delocalized, in this case into sulfur to make a sulfur carbon double bond or a phosphorus carbon double bond. And note that phosphorus can have 10 electrons, so this is not a violation of the octet rule, and in fact sulfur here also has 10 electrons, we're just not showing that lone pair. So these are the ylides of interest in chapter 17. And what we will see is that for the Vinegar reagent, we will use that to convert aldehydes and ketones straight away to alkenes. Whereas for the sulfonium ylides, those will be used to convert a carbonyl to an epoxide. In either case, they fit right in with what we've been talking about already. Like Grignards and like organolithiums, these are strong carbon nucleophiles, carbon anions, that react readily with those polar pi bond electrophiles. Okay, so we'll start with the Vinegar reaction, named after George Vinegar, who won the Nobel Prize for this chemistry. It's a fantastic way to make alkenes. Basically, what happens is you take a ketone or an aldehyde, you add the Vinegar reagent, the phosphonium ylide, and voila. It's just like you cut off this piece and cut off this piece and kind of just smash the two together. So this just sticks right on there, and there it is. There's your alkene. So kind of think about it as like Tinker Toy chemistry. Where does the oxygen go? Well, the oxygen gets stuck on the phosphorus, and that's actually a pretty important driving force for the reaction. Here's another example. This reagent should look kind of familiar to those of you who are in ITR. Basically, this is not acetylferrocene, but it's the aldehyde variation, so Vinegar reactions work fine with aldehydes as well as ketones, and again, I'm just showing it in a slightly different manner. You are using this piece to connect right here to make the alkene. So again, that's just the resonance contributor for the Vinegar reagent. And so that piece just slams right onto the carbonyl and sticks to make the alkene. How does it work? Well, the mechanism, it makes sense if you break it down step by step and think about electrophiles and nucleophiles. And to do that, you really need to ignore this version of the Ylide and think instead of this version where the reactivity of the Ylide is so much more obvious. It's a carbon anion, and as a carbon anion, it is going to go over here and, of course, react with the electrophilic carbon of our polar pi bond. So, as long as you write this resonance contributor of your Ylide species, it's pretty easy to see what the first step of the mechanism is. So, that step leads us straight away to this. We've now made a new carbon-carbon bond, and I'm just taking this molecule and redrawing it, bending the carbon-phosphorus bond up 90 degrees so that you see what's going to happen next. Makes perfect sense. I've got this nucleophile, and intramolecularly I have an electrophile. Remember, we can violate the octet rule as much as we want with phosphorus because it has d orbitals. So the oxyanion reacts rapidly with that phosphonium electrophile and gives you this thing. Okay, so here's some of the fun, wacky nomenclature. The ring-opened version here is called a beta-ene. So I know it looks like betaine. It's not betaine. It's beta-ene. And the ring-closed version here, this little four-membered ring, is called an oxyphosphatane. So you can always impress your humanities majors friends by just throwing around these names and say, well, we talked about oxyphosphatanes today in class or online, whatever. So, well, we're not getting very close to an alkene, but actually we are. So we've clearly made our carbon-carbon bond right there. How do I get to the alkene from here? Well, remember I told you that phosphorus-oxygen bond was pretty much the driving force for this reaction. And I'm showing the next step in a slightly different way than the textbook does because it's still a matter of some debate as to what the exact mechanism is. But if you look at how I've done this, the four-membered ring collapses to give you the phosphorus-oxygen double bond there, and this pair of electrons slaps down to make the carbon-carbon double bond, the alkene product. So, again, the fact that you're making this really, really robust and thermodynamically stable phosphorus-oxygen bond, that drives the reaction forward and gives you your product. Alright, another example. Let's look, for example, at this 2, 4, 6, 8, 4-octanone reacting with this Vinegar reagent, and you should be aware that Vinegar reagents can have, all kinds of things connected here. It can be a longer carbon chain, it could be an ester, there can be all kinds of different functionality on your Vinegar reagent. Basically, reaction of this Vinegar reagent then, let's just kind of highlight the whole piece. I'm going to add that carbon-carbon piece right here, put the two pieces together, and so there's my 2-carbon piece. I just made the new alkene, but I want you to look at this product and wonder, well, what else might be formed? And I don't mean the triphenylphosphonium oxide. What I've done here is I've given you an example where we have the option of E and Z isomers, and that is kind of a problem with Vinegar reactions. There are ways to control the stereochemistry that are well beyond the scope of this course, but be aware that sometimes if you're carrying out a Vinegar reaction, you may have 2 different isomeric products. And of course you would see that as, for example, 2 peaks in your GC, or 2 peaks in your HPLC, etc. Alright, so what else? Well, it's worth looking into how these Vinegar reagents are prepared, because you know what? It's an excellent review of stuff that you've already learned. First, a good old-fashioned review of SN2 with this great nucleophile and our typical electrophilic alkyl halide. So, the first step in preparing a Vinegar reagent is to react the phosphine of some description. We typically use triphenylphosphine, and just do an SN2 with an alkyl halide. Then, in a second step, you take that charged species, the phosphonium salt, and deprotonate it to make the carbon anion that is the ylide. So let's look at an example here. If I take this ester and convert it to this bromo ester, well, you should know how to do that. I can then react the bromo ester with my phosphine, and that preferentially attacks at the carbon bearing the leaving group, the halide, to make my phosphonium salt. So my Br minus is the counter ion. And if you're wondering, this was, at the end of fall semester, you need to use Br2 under acidic conditions to make the enol, which can then react with the bromine to brominate at the alpha carbon. Alright, well, once you have made the phosphonium salt, then all you have to do is deprotonate, and you've got your ylide. So basically, strong base rips off that alpha hydrogen, and there you go. There's your ylide. And that can then be used to make a new alkene with an aldehyde or ketone. So that was the Vinegar reaction. Once you got that down, everything's peachy keen until you get to sulfonium ylides, and you think they should do the exact same thing, but unfortunately they don't. So sulfonium ylides have the exact same first step, but the outcome is a little bit different. So here's my sulfonium ylide. It reacts with an aldehyde, but as you can see, I do not get an alkene, I get an epoxide. The first step is the same, reaction of the nucleophilic carbon anion with the electrophilic carbonyl. So what the heck is going on? Well, to understand what the heck is going on, we need to look at the mechanism, which means electron movement, nucleophile, reacts with electrophile, reacts with the polar pi bond, kicks up the pi electrons onto the oxygen, as we would expect, to make this intermediate. Wow, that's a pretty hairy intermediate. And obviously you would probably think that, well, it would be just like the Vinegar reaction, where we'd get that four-membered ring and blah, 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 blah. But actually it doesn't work that way. And we have to pay attention to the data and the reality of what we do get. And what we do get is this epoxide. So how is that formed? Well, it's formed in a really very reasonable, mechanistically sensible way, because if you consider that sulfonium ylide piece that I've just circled, well, that's a really good leaving group. It's a great leaving group. And so instead of attacking the sulfur, the oxygen attacks the carbon and kicks that out to give you your product plus the nice weak base, the disulfide. So that's how sulfonium ylides react to make epoxides. Alright, stands to reason we should learn how to prepare sulfonium ylides, and that is exactly the same as phosphonium ylides. It's again just an SN2 reaction. Reaction at the electrophilic carbon, kick out the iodide leaving group. So I have this sulfonium salt with an iodide counterion, and then the excuse me, the base, pick a base, any base, it could be sodium hydride or another base like N-butyllithium, deprotonates that hydrogen adjacent to the positive charge, pretty acidic, and that'll give you your ylide, just like you would expect. And again, this is just one resonance contributor. If we slide those electrons up in there, we end up with this version. So, even written like this, remember, that guy is a nucleophile. I want to point out one other thing that's really kind of important and a little bit of questionable aspect of your textbook. Note that in this example, there are no hydrogens that can be removed. So when it comes to deprotonating the sulfonium salt to make your ylide, there's only one place for the sodium hydride to go, and that's right there. You'll note in your textbook that there are typically sulfonium salts that are all bearing the same kind of alkyl group. If that's the case, then again, there's no question about what ylide structure will result, because all three of these are exactly the same. But you need to be aware if you have, say, an ethyl group and a methyl group and another methyl group. Well, either one of these hydrogens could be removed, therefore ending up with a mixture of products when it comes to adding your ylide to your carbonyl. Okay, so as you can tell, you can probably tell I'm just choking here. So what I'm going to do is put this example up here and run through it pretty quickly. It's great review for you. Basically, taking a diol, reacting it with this, gives you the mesylate. You should be able to predict that product, again, by looking at the fact this is a good leaving group, electrophile, nucleophile. I'm going to kick out that chlorine and get the dimesylate because I've got two equivalents. Well, what you've done is you've made a tremendously good leaving group. Mesylate, mesylate, they both want to leave, and of course if I cross out my spectator ions, I've got, wow, a -2 charge on my sulfur. So that should lead me to think that I'm going to get a substitution. Well, can you figure it out? If I get a substitution with a 2-, hey, very cool. What I've done is I have done an intramolecular substitution reaction to give me, wow, is this cool or what? A chiral sulfide. Well, that means I can use this to make the sulfonium ylide, because just like any other sulfide, it'll react in an SN2 reaction to give me the sulfonium salt. Sulfonium salt then gets deprotonated what do we get? Well, you get the chiral ylide, which then reacts with the aldehyde. Cool beans, you get the epoxide, but you get it with stereochemical control. Now, you don't need to know about the stereochemistry. There's no way you can predict whether you're going to have this epoxide or the one where the epoxide is going back behind. But you should be aware that scientists are always trying to improve upon synthesis and be able to control the stereochemical outcome of reactions. So, this is a great example of the sulfonium ylide chemistry and formation of that epoxide, as well as an example of how we try to control stereochemistry to get a favored outcome of one enantiomer over another. So, very cool. That's it for ylides, and we will get on to the next topic in the next mini lecture.